In this lecture set, we will go through an economic application of optimization theory. So in particular, we will be going to the problem of utility maximization. And so in this problem, there is a consumer with a certain income, okay, a budget, so to speak. And his problem is that he wants to allocate the budget to spending on two goods, okay, on a number of goods, but here we'll just concentrate on two goods, which we label capital X and capital Y. Okay? And the consumption of good X is denoted by this small letter x, and the consumption of good Y is denoted by small letter y. So small x and small y are the quantities consumed by this person or this individual or this consumer. Okay? Further, we assume that x and y only admit non-negative values. Okay, so he can either consume zero, which means he consumes nothing, or he consumes a positive amount of x or y. So this rules out negative consumption, okay, whatever that means. So, like I said, consumers have preferences over goods or bundles X and Y. So, for example, the bundle is two apples and one banana versus one banana and two apples. Okay, so the consumer has preference over those bundles. And that preference is represented by a function, which we call U or the utility function. Okay, so the utility function in this case, since there are two goods, maps consumption of those two goods to a number. It spits out a number, okay? And that number reflects the utility or the satisfaction that the consumer has over those bundles, okay? So if the utility at xy, okay, is higher, or the number in the function u that it spits out, that the function u spits out, is larger than the number that the function u spits out in another alternative bundle, x prime, y prime. This means that this consumer prefers or strictly prefers the bundle xy to the bundle x prime, y prime. Okay? So the bundle could be like, say, two bananas and one apple. So two of x and one of y versus, say, one of x and three of y. Okay? So if the number that you spits out from this bundle is higher than the number that you spits out from this bundle, then the consumer strictly prefers the bundle xy to the bundle x prime y. Okay? And if the utility function spits out a number when you enter xy, bundle xy, which is equal to the number that the utility function spits out when the bundle is x prime y prime, then we say that the consumer is indifferent between the bundles xy and the bundle x prime y prime. Okay? So if it prefers one bundle over the other, the utility function will spit out a higher number. Okay? If the consumer is indifferent between two bundles, the utility function spits out the same number. Okay, so that's what the utility function is. It's a representation of the preference of the consumer. Okay, so I just jumped what the function u is called, but this is called the utility function. Now, the function u, since it's a function, the utility function u, we assume that function to have the following properties. Okay, first, technically, the partial derivatives of u, which we call the marginal utilities, ux and uy. Okay, so again, ux is just the partial u over the partial of good x, meaning how does utility change when x changes, and uy is just partial u over partial y. Okay, we assume that those derivatives exist and are continuous. Okay. Furthermore, we assume that ux and uy are both positive. Okay, so partial u over partial x is greater than 0, and partial u partial y is greater than 0. So what does that mean? If these partial derivatives are positive, take this first. This means that when you increase your consumption of x, okay, it will give you higher utility. Okay, if this one means that if you increase consumption of y, then it will give you higher utility of higher satisfaction. Okay, so that's the property of non-satiation. Okay, satiation is that you'll be satisfied. Non-satiation is just you won't be satisfied. Okay, if you consume more, you get higher utility. You'll get more satisfaction. So this is just what this assumption is saying. Okay, and we further assume that the utility function u is strictly concave. Okay, so let me illustrate what that means by just one variable. Suppose you only have one good, okay, x, and then you have your utility u of x. So we know that a function is strictly concave if we have kind of like this form, okay? Which means that, okay, if it's strictly concave, notice here, for example, I start with x1 and x2, okay? Okay, so the utility at x1 is u of x1, okay? And the utility at x2 is u of x2. Notice that when you increase your consumption from x1 to x2, okay, your utility will increase by this much. Okay? So this is the height at which your utility increases. Now suppose you increase by the same amount to x3. So the jump from x1 to x2 is the same as the jump from x2 to x3. Okay? Say this is 1 unit. Okay? x1 to x2 is 1 unit, x2 to x3 is 1 unit. And then the associated utility at x3 is u of x3. Okay? Now what do you notice? You notice that the jump between u of x2 and u of x3 is now this high. Okay? So this length over here is longer than this length over here. Okay? So the jump from x1 to x2 is 1 unit. It's the same from the with the jump from x2 to x3. So a consequence of assuming a strictly concave utility function is that the more you consume a good, okay, the extra amount of utility or satisfaction that you get diminishes. Okay, so this is another term for this one is diminishing marginal utility. Okay, so again, if you consume from x1 to x2, say x1 to x2 is additional 1 unit, the utility there will be higher than the change in utility will be higher than the change in utility when you consume x3 from x2. Okay? So that extra utility will be that increase. What I mean is this increase in utility will be smaller. Okay, so that's a direct consequence of the assumption that u is a strictly concave function. So now here we'll formally state the problem. So the consumer has a utility function u and a budget b. Okay, and then for goods x and y, the prices are p1 and p2 respectively. Okay, so p1 is the price of good x and p2 is the price of good y. Okay, so now the utility maximization problem, which is the consumer's problem, is to maximize his utility, okay, or maximize his satisfaction by consuming x and y, subject to his budget constraint. Again, you know this by now. What is this left-hand side? P1x is his expenditure on good x, okay? Expenditure on good x. And P2y is his expenditure on good y, okay? So the total expenditure should be less or equal to than the person's budget or his income or his allowance, okay? So prices are positive. We assume that prices are positive and the budget is also positive. And here we have an explicit non-negativity constraint, which says that negative consumption is disallowed. Okay, so this is the consumer's problem. The solution X star Y star that maximizes the utility subject to his budget is called the utility maximizer. Okay, so that's the optimal solution. The X star and Y star will find that will maximize the consumer's budget. So now here we're just rewriting the problem because in the previous slide we had P1x plus P2y less than or equal to B. Okay, so this is a less than or equal sign. We need to write it in the standard form where we have a greater and equal to sign here. So we'll just multiply both sides by -1. Okay, so we have uh, negative b over here. When we uh, bring it to the other side, we have b, then minus p1x plus minus p2y. Okay, then now this is a greater than or equal to sign 0. So this is now how we transform this budget constraint. Okay, we still have the non-negativity constraints here. Okay, so again, um, well, f and g are concave functions. Okay, so we just assume that u, I mean not f but u, we just assume that to be strictly concave. So u is concave, in fact strictly concave, and the budget, this function g of xy of the budget um, is linear, so it's also concave. Okay, so that's satisfied. Now we need to determine whether the constraint G is satisfies the Slater's constraint qualification. Okay, so what did we just say? How do we satisfy that? Well, G is concave because it's linear, and then we need to choose a vector. Okay, in this case, we choose the vector 0, 0. Okay, and then we plug in 0, 0 for x and y in this equation. Now, when you do that, you're left with b. Okay, so if you find such a vector and it produces a number that's positive, then the Slater constraint qualification is satisfied. Okay, okay, so whatever x star y star that we get needs to satisfy the Kuhn-Tucker conditions, necessary conditions. Now, this is just a review. These are the Kuhn-Tucker conditions to your left. Okay, specifically for the problem with explicit non-negativity constraints. Okay, so we have in the first condition fx plus lambda gx. In this case, we have, since f is a utility function, we have the partial of u with respect to x, which is ux, okay, plus lambda, and then gx is the derivative of this function gxy with respect to x. This is -1, so therefore we have a negative lambda p1 here, which is less than or equal to 0. In the same manner, fy over here is just the derivative of the objective function with respect to y, so this is uy, okay, and then plus lambda gy. Gy is the derivative of g with respect to y, which is negative p2. Okay, so therefore we have a negative lambda p2 here, and then we have less than 0. Okay, great. So next condition, let's just erase this one. So in the next condition, we have here in condition 1, the expressions in condition 1. Okay, so this 1 we have to multiply by x, and that will be equal to 0. So it's either x is 0 or the term in the bracketed or in the parenthesis is equal to 0. Okay, and if and the second condition here is just this expression over here times y. Okay, so you equate that to 0, so it means that either y equals to 0 or this expression in the parentheses equals to 0. Right? And this third condition is uh, lambda g, the function of the budget constraint, should be equal to 0. So it's either lambda is equal to 0 or this term in the parenthesis equals to 0. Okay? Then you have lambda being non-negative, and then you have the function g, the budget constraint, being greater or equal to 0, and then finally we have the non-negativity constraints. So those are the Kuhn-Tucker conditions specific to this problem that we had, this utility maximization problem that we have. Now, before we specifically solve this or go to an example where we can solve this utility maximization problem, we'll just analyze first the Kuhn-Tucker conditions in some cases, okay? So suppose we assume that x star y star is the utility maximizer, meaning that x star and y star will give you is the consumption that will give you the highest utility, that will give the consumer the highest utility, okay? And suppose that both are consumed in positive amounts, okay? So from this condition, from condition 2, since x and y are positive, then this term in the parenthesis should be the one equal to 0 because this should hold. Okay? So in this case, x star y star minus lambda star p1 is equal to 0, and uy x star y star minus lambda star p2 is equal to 0. Okay? So what we can do here is we can solve for lambda. So in this case, lambda star is equal to ux x star y star, sorry about that, x star y star over p1. And then from this one, we have that lambda star is equal to uy x star y star over p2. Okay? So here we would just rewrite what we had scribbled in the previous slide. So we have ux p1 over p1 is equal to uy over p2. Okay, so this is the marginal utility per peso, okay, of per peso of good x, and this is the marginal utility of y per peso of good y. Okay, so if x and y are x star and y stars, x star and y star is the utility maximizer, then this ratio, ratio of the marginal utility with the price or the marginal utility per peso should be equal for both goods. Okay, so marginal utility of x divided by p1 should be equal to the marginal utility of y divided by p2. Or we can rewrite. So here we have the condition that we had earlier when we solved for lambda. So we can put uy here, okay, and then p1 we could put in this numerator. So you end up with the expression ux over uy is equal to p1 over p2. Okay, so this is the ratio of the marginal utilities for good x and y. And this is the ratio of the prices of good x and y. Okay, so at the optimum, when you have a utility maximizer, okay, in order for this x star and y star to be a utility maximizer, the ratio of the marginal utilities at x star y star should be equal to the price ratio. Okay, so just anticipating our results later, this is important because this represents the slope of the what we call the indifference curve. Okay, so the indifference curve is just a level curve for the utilities. Okay, and then P1 over P2 is just the slope of the budget line. So we will apply the implicit function theorem as we shall see later. Okay, so just bear this in mind, just keep this in mind that the ratio of marginal utilities is the slope of the indifference curve, and the price ratio is the slope of the budget line. We will see that more clearly in the next few slides. Now, as we have just shown, lambda star is equal to mu x, x star y star over p1, which is also equal to mu y, x star y star over p2. Okay? Now notice that the marginal utilities are positive. Okay, this is positive. The prices are positive. Okay, and yeah, so this is positive. This is positive. So therefore, lambda star is also positive. Okay, lambda star is a positive number. So if that's the case, by this condition, condition 3, since lambda here is positive, the only way for this equation to hold or to be equal to 0 is when this term in the parentheses is equal to 0. Great. So in order for this to be 0, this should be happening. Okay. So p1x plus p2y should be equal to b. Great. If that's the case, then b minus p1x minus p2y is equal to 0. Now, what does this mean? Okay. Again, since we have an equality sign over here, okay, since we have an equality sign over here, it means that total spending on goods X and Y at the utility maximizing bundle should be equal to the budget. Okay, so this person should not save any money. Okay, everything, his budget will be exhausted. Okay, he will spend everything allowed by the budget, and he won't leave money in the table. Okay, so this is the consequence of the X star and Y star being utility maximizers. So if that's the case, when you have positive values of consumption for X and Y, and we know that at the optimum, uh, the person will just spend all his budget, then the utility maximization problem that we had can be boiled down to maximizing the utility subject to this budget constraint. Now, this holds with equality. Okay, so you can do the Lagrangian multiplier method, but this is a consequence of the Kuhn-Tucker conditions when you have X star and Y star positive. Okay, so the person will exhaust his budget, so to speak. Again, this is a graphical representation of the utility maximizing problem that we had earlier. So you know that this budget, this kind of like purplish line over here, is called the budget line. Okay, so this budget line is actually a level curve. Okay, just a review, each point on the budget line. Okay, so this is, for example, x1, y1, and this is x2, y2 on the xy plane. So all these points in the budget line will give you an expenditure equal to b. Great. So this is a level curve, or yeah, where combinations of x and y um, via this linear function will be just equal to b. Okay, great. So in short, p1 x1 plus p2 y1 is equal to b. This corresponds with this bundle. Okay, and this bundle, uh, p1 x2 plus p2 y2. Okay, at the bundle x2 y2, that expenditure, the total expenditure, is also equal to b. Okay, so that's what the budget line is. Points on the budget line are combinations of x and y, are bundles that uh, that give you an expenditure equal to your budget. Great. Okay, so let me just clear this thing. Now, what are these red lines over here? These red lines are what you call indifference curves. Okay, so like I said a few slides ago, the indifference curves are level curves. Okay, so they are level curves of the utility function. Okay? So What does this mean? So for example, let's take this point here, okay, in this indifference curve. So let's call this point x1, y1, and this one x2, y2. Where does the term indifference curve um, come from? Well, since this is a level curve, all points in the indifference curve will give you a certain utility level. So call this U naught, this higher indifference curve U1 is equal to U1, and this one is U2. Okay, so at point x1, y1, so U of x1, y1, okay, will give you a utility level U naught. Great. So points in x, this point x2, y2, okay, so x1, y1 is here, x2, y2, so the utility when you plug in x2, y2 will it'll also give you u naught, okay, because they are points in the level curve or the indifference curve. That's where the term indifference curve comes from, because the consumer is indifferent between consuming x1, y1 and x2, y2. Why? Because it gives him the same utility level, u naught. Okay? So it's actually indifferent between those two bundles. So the points on the line, the indifference curves, are bundles that will yield the same uh, level or amount of utility. Great. Now in this case, the higher the level of u, the higher the level of the indifference curve, the higher the level of utility. So in this case, u1 is bigger than u0, but u2 is biggest among u1 and u naught. Okay, great. So again, just to hammer in the point, suppose we have 2 points here in this thick red indifference curve. Call it x3, y3, and this one is x4, y4. Okay, so the utility at x3, y3 would give the consumer u1. Okay, the utility at x4, y4 would also give the utility u1. Okay, u1, u0, and u2 are just numbers. Okay, so since they give the same utility, then the consumer is indifferent between this bundle and this bundle. Okay, great. Now the question is, uh, well, first before going there, you know that this problem is equivalent to finding the indifference curve that's farthest from the origin that touches the budget line. Okay, so you're finding the highest utility subject to your budget. So the indifference curve that just touches the budget line achieves that. So yeah. So what do you notice? So at that point, x star, y star, where the indifference curve touches the budget line, of the slope of the budget line is just equal to the tangent line at that indifference curve. Great, good. So the question is, what is the slope of the budget line? Well, from the implicit function theorem, that's just g of x divided by negative g of x divided by g of y. Okay? So that's equal to negative p1 over p2. Okay? And what is the slope of the indifference curve? Well, the slope of the indifference curve, since this is a level curve, this is just equal to the partial of u with respect to x divided by the partial of u with respect to y. Okay, so um, just brush up on the implicit function theorem, okay, on finding the slopes of the level curve. So this is just equal to ux over uy. Okay, by the way, there's a negative. Okay, great. So since the slopes are equal, we have that negative mu x or mu over mu uy is equal to negative p1 over p2. Okay? Since both sides are negative, we can cancel the negative sign. Then you have ux, uy is equal to p1, p2. Have we seen that before? Yes. Okay. Go back one slide. This is the condition for optimality, precisely the condition for optimality. So just to reiterate what I said, at x star y star, so this is x star y star. Let me just write this here. So this is x star and this is y star. Okay. So at that point, we have just shown that the slope of the budget line is equal to the slope of the indifference curve that just touches the budget line. Okay, so again, due to the implicit function theorem, the slope of the indifference curve is negative ux divided by uy. Now we evaluated at x star y star. Okay, and the slope of the budget line, again, due to the implicit function theorem, we have negative p1 over p2. So at x star y star, since these slopes are equal, then we have ux over uy, okay, evaluated at x star y star, okay, is equal to p1 over p2. So just to reiterate, this is the condition for optimality that we had a few slides back. So that's how you think about the utility maximization problem graphically. So let's go back to the Tucker conditions. So we have here, since we assume that x and y are consumed in positive amounts, then from this condition, from condition 2, since x and y are positive, then this term in the bracketed, in the parenthesis should be equal to 0. So this is the first two conditions over here. Now we have shown that since marginal utilities and the prices are positive, then lambda should also be positive. And if that's the case, if lambda is positive, this one is positive, then the only way for this equation to be 0 is when this term in the parenthesis equals to 0. So this is this equation over here. So what do you notice? Here we have three equations and three unknowns. We have unknowns x, y, and lambda. And the x star and y star and the lambda star that would satisfy this three equations simultaneously is the optimal solution. Okay, great. Now let the solution x star, y star, lambda star be uh, such. We know that x star, we'll show it via an example later, but the optimal solutions x star and y star and lambda star are functions of the parameters p1, p2, and b. Okay, so if p1 or p2 and b changes, if either the price or the income or the budget changes, then the optimal value of x star, y star, and lambda star will also change. Okay, so this is dependent on a particular level of p and b. Great. Now, that function, x star, which is a function of p1, p2, and b, and y star, which is a function of p1, p2, and b, or of the prices and income, are called Marshallian demand functions. Okay? Okay? So those utility maximizers, x star and y star, are also functions of prices and income. Great. We'll show an example later. But just remember that those optimal values, x star and y star, are also functions of prices and income. Okay, so when prices change and the income changes or the budget changes, then the optimal value of x star and y star will also change. Now we'll go to a property of Marshallian demand functions. So suppose that we have a k-fold increase in price. Okay, so if k equals to 2, it's a twofold increase in price, meaning prices and income double. Okay, so suppose there's a k-fold increase in prices and income simultaneously. So if k equals to 2, then prices and income have doubled at the same time. Okay, so if that's the case, then our new prices would be kp1. So if, for example, your original price of good X is 2 pesos, now it's 4 pesos. Okay, if k equals to 2. So kp2 is the new price for good Y, and kb is the new income or budget. Okay, so all prices and income or budget increase k-fold. So what do you notice? Well, in the maximization problem, you have the same maximize u of xy, and in the budget constraint now it has changed because KP1 is now the new price of X, KP2 is the new price of Y, and KB is the new income. Okay, so what do you notice? So since this should be greater than zero. Since K is greater than zero, then we can just cancel all the K's here in the budget constraint. Okay? So if that's the case, we're back to P1x plus P2y less than or equal to B. So what does this imply? We're back to the original problem. So therefore, the bundle utility maximizers x star and y star wouldn't change. So the solution to the problem where prices and income increase k-fold simultaneously is the same as the solution to the original problem, to the old problem, where prices and income didn't change. Okay? So therefore, what we have is that your optimal values of x and y under the new income and prices, okay, that's the KP1, KP2, and KB here, is the same, since this is the same problem, is the same as the utility maximizers in the original problem where we have P1 and P2 and B as the original prices and income. Okay, so this amount, X star, is the same. Okay, Y star is the same. So this is equivalent to saying we have K raised to the zero, which is equal to 1, before X star, Y star. Okay, so recall, what if you have a function of F, say Kx, and then Ky is equal to K not the same function f of xy. So this function is homogeneous of degree whatever is the exponent here. Okay, so since the exponent is 0, we say that the Marshallian demand functions x star, k, p, and b. Okay, the Marshallian demand functions x star and y star, which are functions of prices and income, are homogeneous of degree 0 in prices and income. Okay, so that's the same as just saying that if prices and income increase in the same proportion, okay, that wouldn't change the optimal bundle. Okay, so consumer demand is free of money illusion. So again, just to remember, the point is that the Marshallian demand functions are homogeneous of degree 0 in prices and income. We'll go through an example later on. So now we have a utility function u of xy. Okay, so that's our utility function. And then we have our optimizers x star, which is a function of P1, P2, and the income or budget B. And then we have y star, which is also a function of P1, P2, and the budget or income B. Now, when you plug in x star for the x here and y star for the y star for the y here, we get a special kind of utility function. Okay, so this special kind of utility function where we just plugged in x star and y star for x and y gives you u star. Okay, since x star and y star are utility maximizers, u star here is the maximum utility that you can attain given prices P1, P2, and your income B. Okay, so for certain levels of prices and income, u star over here is the maximum utility that you can achieve. Okay, so this is a special name. This is called the indirect utility function. Now, where does the term indirect means? It's just from the fact that in your original utility function, u of xy, it's a direct function of consumption levels x and y. Okay, so if you consume x, you get satisfaction. If you consume y, you get satisfaction or you get utility. Okay, now it's indirect because instead of the consumption bundle xy, we have the prices and the income, okay? P1, P2, and B. So this says that if your income or your prices change, the utility or the maximum utility that you derive, okay, will also change. Okay? So that's why there's a that's where the term indirect utility function is. It's just um, it's just because the utility function is now a function of prices and income instead of the direct consumption bundles or direct consumption of X and Y. Now we shall show that this indirect utility function is also homogeneous of degree zero in prices and income, because since we have this as our definition of the indirect utility function, you just plug in X star and Y star to the utility function. Okay. Now suppose uh, we change prices and income by the same proportion K. So this is the new price of good X. This is the new price of good Y, KP2. This is the new income K, KB. Okay. And we have shown a few slides ago that the optimal consumption of X and Y doesn't change because X star and Y star, the Marshallian demand functions, are homogeneous of degree zero in prices and income. So X star, KP1, KP2, KB, okay, is equal to X star, P1, P2, and B. Okay. So if that's the case, that's the same also for Y star. So Y star, KP1, KP2, KB is equal to Y star, P1, P2, B. Okay, so if that's the case, then we can write this here. So therefore, the utility function at the new prices and income is equal to the utility function. This should be U star. Yeah, the utility function at the old prices and income. Okay? Since the optimal values of X star and Y star will not change. So in short, this indirect utility function is homogeneous of degree zero in prices and income. Okay? Same as the Marshallian demand functions.